Welcome to the Grade 10 CAPS Mathematics video series. In this video, you will be given a broad introduction to angles, lines, and triangles. Let us have a look at the outcomes for this video. In this video, the focus will be on basic results regarding lines and angles. This will be done in Lesson 1. Next, we consider classification of angles according to their size. In all cases, we will represent the angle BAC as indicated with the segments BA and AC used to do so. And note, in this case, in general also, one can denote an unknown angle by a symbol. In this case, we use the symbol theta, and normally Greek letters of the alphabet can be used to do so. So we refer to this as the angle theta, of course, represented as the angle BAC in this case. Now in this particular case, we say that the angle theta is an acute angle. This means that the angle, the size of the angle, lies between 0 degrees and 90 degrees, strictly between 0 degrees and 90 degrees. The next representation is that of a so-called straight angle in 180 degrees and 360 degrees. And finally, we have the specific case of the angle with a size of 360 degrees, and in such a case, we refer to such an angle as a revolution. Theta equal to 360 degrees, one full cycle, or a revolution. At this point in time, I suggest that you pause this video, do this second part of tutorial 1, and then come back and view the solutions. Let us consider the suggested solution for problem 4 of tutorial 1. Here we have the problem once again. Here is the sum of the two opposite interior angles in such a case. Finally, the line segments BC and EF are parallel, and these two angles are then also corresponding angles in this situation. Therefore, we know that the angle ABC is the same as the angle DEF and that particular case, and this answers the final part of this particular tutorial. In lesson 2 of this video, we will consider some basic results on triangles. Let us consider the outcomes for lesson. In this presentation in the Grade 11 CAPS Mathematics video series, the focus is on circle geometry 2. 180 degrees, this is theorem 1, while the converse of theorem 1, here we will prove that if the sum of two opposite angles given a quadrilateral, note, not a cyclic quadrilateral, and we know that angle D is equal to angle C, this will imply that A, B, C, D are concyclic. If we secondly have a quadrilateral A, B, C, D, and we know that angles D and C are equal in measure, then this will imply that ABCD must be a cyclic quadrilateral. Or more generally in words, if we have a line segment, like in this case AB, joining the 2 points A and B, if this line segment subtends equal angles at two other points D and C on the same side of it, note, points D and C both lie above this particular line segment, then the 4 points must be concyclic. Proof of the previous conjecture, namely that the sum of the opposite angles of a cyclic quadrilateral is equal to 180 degrees or 280. To assist us in this proof, we draw line segments DO and BO. So remember, we know it's a cyclic quadrilateral, so therefore we can say that angle 1 is equal to to twice angle C, because we know that the central angle is 2 times the inscribed angle. In a similar way, co-interior angles, and given that the two line segments are parallel, therefore their sum must be 180. So therefore angle 1 is 180 minus 85 degrees, or 95 degrees. But angle 1 is equal to angle F, so therefore angle F must be 95 degrees. I just want to mention that the methods that I'm doing here is not unique. You may find a different logical proof, as long as you have logical steps and you have valid reasons for each step. That J is 100 degrees, so therefore I must be 80 degrees. We have come to the end of the second video on circle geometry. Please remember, as we mentioned many times before, is to consult textbooks for additional examples.
In this DVD, which forms part of the 2010 NCS Mathematics DVD series, we will focus our attention on calculus applications. We will now consider the graphical representation of relative maximum and relative minimum values for a function. Consider the graph of the function f as indicated on the screen. In fact, this is a cubic function that is graphed as indicated. Here we have two turning points for the function f. Firstly at the point A with coordinates 1, 4, and at the point B with coordinates 3, 0. Now in this case we say that the function f has a maximum value of 4 at the point A when x is equal to 1. Can you see the output value? The y value is 4 when the input value x is equal to 1, corresponds to the turning point, in this case a maximum at that point for the function. In fact, it is referred to as a local or relative maximum at that particular point for this given function. The derivative of the function h is 0 at the x values corresponding to the local extreme points, whether it's a maximum turning point or a minimum turning point. In both cases the derivatives are 0.